Hopefully, we are here discussing. So today we are discussing about quantization process. So simply, in a rough definition, if you want to say, the quantization, what we are doing, we are trying to convert a continuous time signal, which is sampled, got sampled. You can see here, we are getting here x of nts, not x of t. X of nts, it is a sampled version of x of t. Now that we are applying as applying to input to the quantizer. So that is going to give us such kind of a step kind of signal. Means we are converting this x of nts into xq of nts. So let us assume that we got the continuous time signal x of t ranging from VL to VH divided into 8 equal parts. You can see here del naught to del 7, delta naught to delta 7. Delta it will indicate the step size. Okay. So here you can see x of nts is here and xq of nts is this step 1. And these are the time periods where each of the your samples are coming here and occupying some specific values. So what is happening is there, the main difference between the sampling, in sampling, simply we are cutting down this continuous time signal into samples. And whatever the samples now we are getting, that is x of nts, in quantizer, what it will do, it will simply assign some approximated near, near or close value for each sample. You can see here 1 volt, 2 volt, 3 volt, up to 8 volt it has been specified. And each of these close value for each of this step is represented in a binary format. Means in quantizer, what we are doing, simply we are trying to assign some close values for each of the samples using some fixed or variable step sizes. As we can see here, we got 8 different steps, delta naught to delta 7. So hence a quantization process is going to be is simply a transformation from sampled amplitude values of message signal, sampled amplitude values in sample signal into discrete amplitude values. Discrete amplitude means some equivalent binary weight or value will be assigned to each of the sampled value. So next you can see, suppose if you take the step size as delta here, so delta equal to, you can take, for example, VL and VH will indicate the highest and lowest value. Continuous time signal. Hello? So the step size, if it is denoted by delta, as you have seen in the last slide, delta naught to delta 7, 8 different levels of the quantization levels we have selected there. So delta step size, we can redefine this one as difference between the highest and lowest, means range of this continuous time signal. The differences will take divided by L, it will indicate 2 to the power here. R, it will indicate the number of bits here. So the step size will be redefined as the ratio of difference between the two ranges of the continuous time signal divided by 2 to the power R. It is L. So if a same step size is maintained throughout the process and is known as uniform quantization. As you can see in this diagram, the step size will be remaining same here. So that is known as uniform quantization. And if you get any difference between this x of NTS and x of NTS, that is known as a quantization error. So that normally varies from plus delta by 2 to minus delta by 2. So next we can see the quantization noise. So there is a random error that is occurring randomly because of this quantization process it is happening. Produces a noise at the output of quantizer. So there are two types of impacts we are getting because of this quantization. First one is a mid-thread type of quantizer, another one is mid-riser type of quantizer. So if you look at these two diagrams, it is very much clear that how the mid-thread and mid-riser type of quantizers are going to differ. If you look at the x-axis, it will indicate in the mid-thread type delta by 2, 3 delta by 2, 5 delta by 2 and so on. Odd number fractions are there. So those will indicate decision thresholds at which your each of the steps will be allocated. And whereas on the y-axis we got the labels delta, 2 delta, 3 delta like that. So as these are going to occur with respect to the y-axis symmetrically, hence it is also known as split quantizer of mid-thread type. Again the step size will be remaining same, means we can say that it is a uniform quantization. It is a uniform quantization with the step size symmetrically allocated on either side of the y-axis with odd multiples of fractions for the decision thresholds. That is on the x-axis. That's why it is known as a mid-thread type. Whereas in mid-riser type, it is just exact opposite to that of the mid-thread type. So here you can see the decision thresholds are going to be an integer multiples, not fractions. Not fractions here. And whereas the quantization levels will become odd multiples of fractions. So this is one thing we can differentiate between these two, mid-thread and mid-riser type of quantizer. So main point what you have to remember here is that decision thresholds in case of a mid-thread type are going to be odd multiples of fractions on the x-axis. Whereas in mid-riser type, these will become on the y-axis, that they will become the quantization levels. So next one, I will try to understand quantization noise a little bit. So what is quantization noise here? The difference between these sampled signal and quantized signal. That is x of NTS and xq of NTS. If some difference will exist, no, as it has been shown here with the dotted line error, so that is going to vary with respect to time randomly. Here it has been shown here. So let the random variable q denotes the quantization error, this one, which is varying with respect to time with the q its sample value. So sample value q it will indicate the difference between m and v. M here you can assume it as input signal, that is sampled input signal x of NTS, and v you can assume it as output of the quantizer, that is a quantized output signal. So consider then an input signal m of a continuous type varying from minus mx to plus mx, and the step size of the quantizer is given by twice the plus mx divided by L, that is L means 2 to the power R. So now the PDF of the quantization error Q given by FQ of Q equal to 1 by delta varying from minus delta to plus delta by 2. Otherwise, at remaining places it will be 0 only. that is a step function, square pulse occurring at minus delta by 2 to plus delta by 2 with the amplitude of 1 by delta. Means you can imagine as a one impulse is located there. Total area under that square pulse is going to be 1 by delta into delta is going to be unity only. Now the variance of this or such kind of quantization error is given by taking the integration, that is the area under that square pulse or impulse. We'll have to take the area under that single impulse available at minus delta by 2 to plus delta by 2. So q square into fq of q, integrate this one with respect to q here, integrating this subject to condition that fq of q is going to be 1 by delta. That you can substitute here. And next 1 by delta is going to be a constant thing that to keep it outside, and integrate q square with respect to q. So that will become q cube by 3, varying from minus delta by 2 to plus delta by 2. And if we simply apply these limits and resolve it, so finally we are getting it as rho q square equal to delta square by 12. That is known as mean squared quantization error, or also known as normalized noise power or quantization error in terms of the power. This is called as equation number A. We denote this one by equation number A. So this is a very important derivation we are doing today for the quantization noise. Next, continuing this one, so let us consider R denoting the number of bits per sample. Then quantized level is given by L equal to 2 to the power R. Now we can substitute this 4 into here, equation number 2, delta, that is the step size is given. That will become 2 max by 2 to the power R. Now call this equation number 5 and substitute this 5 in equation number A here. So this equation number A, that is for delta. Now if you substitute here and simplify, finally we are getting mean squared error as 1 by 3 times m max square, that is a positive maximum range of the continuous time signal square, into 2 to the power minus 2r, that is 1 by 2 to the power 2r. So let P denotes the average power of the message signal m of t. Then output SNR of the uniform quantizer is given by P by rho q square. Hello? Yes. Now P indicates the average power of the message signal m of t. Then output signal to noise ratio, that is SNR naught, for the uniform quantizer is given by this formula, that is average power of the message signal P divided by rho q square, that is mean square error, whatever you got. Then we will get a final expression for the output SNR for the uniform quantizer. So this is, guys, very important derivation we have observed today for the uniform quantization. So next one, I want to continue with this pulse code modulation. So here pulse code modulation, we got the transmitter and the receiver. So here what it is happening is that in process it is a message signal which is represented by a sequence of coded pulses, which is actually obtained by representing the signal in terms of discrete form in both time and amplitude. So the basic elements of PCM system are going to be a transmitter and a receiver. So in a transmitter, you can see the source of continuous time message signal is given as input to the pre-aliasing low pass filter. Its main job is to ensure that the samples will not get overlapped. Optimized aliasing or sampling will occur without any aliasing problem. Then those samples will be given as input to the quantizer. So just now we discussed how the quantization process is going to happen. For each of the sample, some predefined known closest value will be allocated by the quantizer. Then it will be encoded, we have seen. So first voltage levels will be assigned in terms of a quantizer, like 1 volt, 2 volt, 3 volt, 5 volt. Then those levels will be encoded by using binary or some BCM coding, that is known as encoding. Then PCM signal applied to the channel input. Now distorted PCM signal, now it is here you can see it is transmitted through the transmission path with help of PCM, pulse code modulation. Here you can see throughout the transmission path we got only regenerative repeaters are there. This is because in view of the long length of the transmission path. So these regenerative repeaters, what they are doing, as the name suggests, as the signal has to travel a long distance, its power is going to reduce after traveling a certain distance. Then it should be amplified and it should be retransmitted. That's why these are known as regenerative, means your weak signal which is to be transmitted is to be regenerated and repeated, means retransmitted to the next repeater on the path until it will reach the receiver. So finally we can get here regeneration circuit will be there, that is going to extract back our transmitted signal, that is encoded signal, encoded PCM signal. Then it will be decoded and reconstructed. So reconstruction reliability depends on the quantization and sampling, how reliably you have done. Then we are going to receive our original message signal. So in the next session, we are going to discuss these things in detail.